So it's my pleasure to introduce Dr. Michael Atkinson. Dr. Atkinson is the faculty advisor for the Marine Energy Program in the Mechanical Engineering Department at North Carolina A&T State University. His research interests include computational fluid dynamics, integrated design, marine energy, and artificial intelligence. Prior to joining North Carolina A&T State University in 2018, his professional career spanned over 14 years in industry and government, including research laboratories such as GE Aviation, Air Force Research Laboratory, and Naval Air Systems Command. He earned a bachelor and master's in mechanical engineering from North Carolina A&T State University and a PhD in aerospace engineering from the University of Dayton. Welcome.
Thank you. Thank you. Let me go ahead and share my screen. All right. Can everyone see my screen? Good. All right. So thank you for the introduction. As was mentioned, I am the faculty advisor for our marine energy program here at A&T, which is a relatively new program that I started back in fall of 2018. And our focus today is going to mainly focus on or discuss some of the wave energy devices that we've developed, as well as incorporating transdisciplinary education into the program and curriculum at North Carolina A&T. So a brief background about North Carolina A&T. Most of you probably know this, but we are an HBCU, so historically Black college and university. We are the largest HBCU in the country, and we are ranked #1 in terms of public HBCUs in the country. And one of the things that we pride ourselves on is our engineering degree program, or College of Engineering. We are #1 in terms of awarding degrees to African-American engineers, as well as #1 in terms of African-American female engineers in the country. And you'll see that reflected in some of the slides that I'll show later on. We have a very diverse group of students that I work with. And this little picture down in the right-hand corner is our new engineering building. It's the first engineering built in the past 30 years. It's going to be online fall of 2021, so we're all excited about this new building. Within the mechanical engineering department, one of the things that we pride ourselves on is our capstone project. So we have a broad range of senior design projects, going from building model planes to autonomous vehicles. More recently, we've introduced rocketry as well as drone senior capstone projects. But when I joined the department back in 2018, there was nothing revolving around renewable energy. I did not have a background in renewable energy. I'm an aerospace engineer by trade, but students kept asking me, "Hey, Dr. Atkinson, can we do something with renewable energy? Can we do something with renewable energy?" So I said, okay, so let's start, from the beginning. Let's see, what can we do? What are some of the reasons why we would take that up? So some of the students said, depleting fossil fuels. Of course, that is one of the main drivers of this. Climate change is a main driver as well. You can look at this CO2 emissions are the highest they've been in 650,000 years. Global temperatures are up. And we're all familiar with some of the things like solar, wind, geothermal energy, and they're kind of widespread. We see people with solar panels on their homes now. If you do a trip across the country, you'll see wind turbine farms spread throughout the country and throughout the globe. And it's being integrated more into our American lifestyle. In fact, Disney has plans to go, zero net carbon emissions by 2030. And so it's not just, this kind of one-off, thing that we're looking at from the North Carolina Renewable Energy Program, but more of a global effort to look at renewable energy, and it's the future. And this little couple pictures I have, this is a McDonald's that's down in Disney World that I think recently came online. So it's powered by, solar panels and all types of different types of renewable energy sources built into the infrastructure. And here is this, I just really like this picture. It's a solar power plant that's in the shape of course, Mickey Mouse, that's down in Disney World. So this is a global effort that's not just, small scale. So there's larger scale corporations that are interested in looking at renewable energy sources, okay? And so in engaging students, we wanted to explore, what are the other types of energy sources that we can use that are renewable forms. And so they explored solar, they explored wind, geothermal, but they also explored ocean wave energy. And in that, we found out some very unique kind of interesting characteristics and very promising characteristics about it. And so now I'm going to pose my poll question to you, if you have that available. And it's almost a rehash of what George had, so make sure you guys are paying attention here. So current estimates show that wave energy off the coast of the US can potentially meet blank % of total US energy demand. Go ahead and let you guys put that in. This is what I like to do to my students. I ask them a question that was almost already asked to see if everyone was paying attention. But I'll keep moving on, and then we'll come back to it, and I'll give the answer in the next slide. All right. So it looks like we have a lot of people in 42. So moving to the next slide. So the Department of Energy estimates that 2.64 trillion kilowatt hours, which is equivalent to more than 64% of all US electricity consumption, can be met by wave power just off the coast of the United States. And really, if we're able to combine all of the ocean energy resources in the whole world, it's more beneficial than wind and solar combined. So it's very advantageous, but as some of my other colleagues expressed, it's not as well established as solar or wind. So there's tremendous amounts of opportunities from optimization, from an engineering standpoint, as well as policy and regulations, as well as developing your own businesses. And there's a lot of potential for entrepreneurship moving forward. I'm going to minimize this. So as a first year senior design capstone project, what we do at the university is at the beginning of the academic year, all the professors go in front of all of the senior students, and we pitch our ideas, hoping that all the students sign up for our particular program. So me being a first year, this is a new program. I'm competing against more established senior capstone projects. I had this little highlight at the bottom. One of the things that we do here at A&T is that we like to compete, and we also like to disseminate our research. And luckily for the North Carolina Renewable Ocean Energy Program, there's a yearly symposium in which students get to travel and network and interact with people such as Lindsay and George and Mike, and bounce ideas off of each other yearly. And the key point of that, that I really got a lot of students interested in is it's in the Outer Banks of North Carolina. We get to spend a couple of days out there. So that was part of my recruiting tool, along with, hey, we're going to build something cool and exciting. But needless to say, I got a pretty good group of students that first year. And we did actually travel to the beach. And these are some of the students that were able to travel that first year. You can see that they're all happy and that I held to my promise that we would go to the beach. And I want to really highlight here the diversity of the group. So we have female engineers, male engineers. We have graduate students mixed in with undergraduate students. We also have 3 international students. I have a student from Ghana, Bangladesh, and China. So when we came together and met throughout the course of the year, we're able to bounce a lot of great ideas and different backgrounds and diversity, thoughts were able to come in, and we were able to be very successful in that first year. And in fact, in that first year symposium, we placed second place poster in a poster competition. So we were very excited about that. And moving on into the second year, and before I get to that, let me talk about how we were able to be successful that first year. So the first year, we had a limited amount of funds. We were new to this area of research. So we had to be very creative in terms of testing devices. We wanted to focus on ocean wave energy, but North Carolina A&T is about 3 to 4 hours from the coast. So we couldn't necessarily go there to test our devices. So the students beginning in this first year, we wanted to kind of develop what was already out there, what was already available in the market, and see if we were able to improve upon those designs. So we always begin with conceptual design. Basically, it's a student drawing on a piece of paper and saying, hey, Dr. Atkinson, what do you think of this? next thing we do, we go to CAD modeling. And then finally, once we have a CAD model, then we had to build some type of device to test. That first year, we had no equipment. We couldn't go to the ocean. So we actually built little seesaws to simulate ocean movement, to simulate ocean wave conversion devices. Lastly, we built a large scale device. And really, we had 2 students over here that would actually act like a seesaw to simulate ocean waves. And we basically did this, and how this device works, it's in a large mass that's centered around a generator. And as the waves move back and forth, this thing spins around, it's connected to a generator, and we're actually able to produce electricity. Okay. So moving into the second year, and some of the successes that we had in that first year, the students wanted to explore all different types of ideas for ocean wave energy device building. So we looked at electromagnetic buoys, point absorbers. We looked at overtopping devices, even this device right here, which is a cascading waterfall effect in which gravity would generate kinetic energy from ocean water movement. We looked at underwater turbines. But finally, what we settled on, which is known as an oscillating water column. So an oscillating water column acts by, as waves enter a chamber here, which a pocket of air is centered just above the waves, it produces a piston-like motion as the waves come in and out. And as that piston-like motion draws air into a turbine, which then spins and generates electricity. Now, the reason why we chose this device is for a number of reasons. One is that me being an aerospace engineer, I knew how to work with air and turbines and et cetera. Secondly, is that it's one of the most studied devices out there right now. So there's a lot of background information that we could use to draw ideas from, and that students could use to do their background lit search, as well as see if we can improve upon current designs. The first thing that we saw when we looked at this design is that we're saying, hey, from an aerodynamic standpoint, this chamber is very square-like. We have this sudden loss and change of area in terms of pressure loss that we could make more streamlined. So we saw a lot of opportunities to improve upon the current designs of oscillating water columns. So luckily, that second year, our university saw our progress and they saw the students' interest. So they actually invested in us purchasing a small-scale experimental wave tank. How this device works is you see this long chamber here. This long chamber can fill with water, and upstream we have this device right here. That's a motor that's connected to a paddle. And this paddle can move back and forth, basically generating 2-dimensional waves that can travel downstream. With that, we can put in different devices to test out small-scale prototyping for oscillating water columns or even any other type of wave energy conversion device. Also, with that, CSI, which is located on the coast of North Carolina, has this very large scale water tank that we didn't know of the first year, but luckily George, introduced us to it when we went up there for the symposium and gave us a lot of free will to use this device at any time we needed it. So we were able to even build larger scale devices. So this is the second year team. We're able to build a large scale novel oscillating water column, as we like to call it, and test it in the CSI Wave Tank. And here you can see some pictures of that. So this is the the oscillating water column. This is one of my favorite students, Murphy. And these are all the students, or some of the students, getting ready to test our oscillating water column in the CSI Wave Tank. For this first year, we had the chamber here. We had a turbine that's located inside of here. And we were actually able to show that once we turned it on, that we were able to monitor using a tachometer, monitor the RPMs of the turbine. This year, what we're moving to, going into our third year, is actually connecting the generator to the turbine device, as well as a multimeter to see exactly how much electricity we're generating from our devices. So it's a progression each year to show continuous progression in terms of our research and development of oscillating water columns. Just as a caveat, so this test that we did was conducted last year around February 24th. So it was right before COVID hit, and we got in there like the week before the whole university shut down. So we were very luckily able to get in there at that time and test. Now, when the university shut down, we began to focus on using computational methods to assess our oscillating water columns. Doing things computationally, no one has to be together. We can log in remotely. So we were able to use a code known as ANSYS, which is a commercially available code, to test out different changes in geometry to do rapid assessment of these devices. So our first device, we started off with this kind of rectangular device, and we're able to measure, say, our average output versus time at different locations throughout the geometry. So what we would do is we would simply make small changes to the device. We would raise it, lower it, as well as make changes. Here you can see the kind of cobra duct, or this more streamlined shape. We were able to actually produce an order of magnitude higher power compared to conventional designs. And this kind of opens up a design space to us where we can explore many different ideas without having to deal with some of the COVID restrictions. So a lot of our efforts this year have been focused on computational design. Now that the university is beginning to open back up a little bit more, we're able to do more experimental testing, and hopefully we're able to get back to CSI and do large scale testing later on this semester. A second piece of this, and where we plan on moving to in the future, is doing what's known as transdisciplinary education. So everyone's heard of, multidisciplinary education, where we do mechanical, physics, electrical, computer science. But another piece that's missing, particularly when we start talking about ocean renewable energy, is that it's a global effort. Last year, I teamed up with a tour group known as EF Tours, educational tour group. We actually took a trip to Spain and Portugal for a week last year, and we were actually able to tour a oscillating water column facility located in the northern coast of Spain in the Basque region. And it's one of the very few oscillating water columns facilities in the world. So being able to travel there and actually visualize it for students, I think was very beneficial for their education. And not only do we want to incorporate engineering and the technical things, which most engineering students have a good handle of, is we want to be able to begin to develop entrepreneurship collaboration. One of the things that we do at our university, and I'm trying to really pioneer this effort, is for our students to work with community makerspaces. Makerspaces are popping up throughout the country. This one in particular is located in downtown Greensboro. This was probably in February, so just before COVID really put things in a crunch for us. But we were able to go there, and what you find is that you'll have, old retirees, you'll have, high school students with just a multi-faceted areas of interest and expertise that really helped us develop some of our methods moving forward. And this last piece over here is us working with Impact Hub in Madrid. Impact Hub is a global entrepreneurship networking company that's what they're devoted to do. So we're able to go there in Spain and actually interact with different people from the Spanish government to see how they would handle global energy impacts. And what we found is very different from how the US does it. So engaging students in that way, I found, was very beneficial. This is just some of the highlights. I know my time is probably coming to an end. So I'll just kind of say, we have a lot of undergraduate students involved in this program, PhDs, masters. We publish as much as we can, journal articles, poster presentations, and we do win awards ranging from Department of Energy awards to MIT awards as well for our research. We also really pride ourselves on additional partnerships. And with that, I close. I do have some references here, and I can talk about these at a later time. But I know I'm out of time. I tend to be long-winded, so I'll take any questions.
Thank you, Dr. Atkinson. So there are a few questions in the Q&A. Regina asked, what's the turbine attached to, or does it float free? And how would it handle storms?
Oh man, that's an excellent question. So that's one of the things that we're actually working on right now, but really how we attach it, we have a shaft that the turbine is connected to, that it spins, and that's connected to a generator. Last year, when we did it, the turbine actually floated free and it fell out a couple times. So this year they found a kind of smart way to make a hollow shaft in which they place a rod through, and it's kind of cantilevered off of the upper portion of the chamber.
Thank you. There's also some questions about the capstone project. Does every engineering student do such a project, or is it just the honors students? And then the other question was, were the designs and the computational work of the capstone part of the competition, or was that separate from the competition?
Okay, so first, yes, every student in the engineering program has to do a senior capstone project. They differ in terms of level of difficulty. So I would say the mechanical engineering, I'm rooting for my department here, has the best capstone projects. But yes, any student coming through A&T's engineering program has to do a capstone project. What was the second question?
Sorry about that. It was just asking about the senior capstone project. Were the designs and the computational work part of the project or part of the competition, or both?
Neither. So it wasn't part of it. It wasn't required, but that's what, at least I think, what I think is beneficial for design and teaching students, not just to be experimentalists, but also to be computationalists as well, so they get a more rounded education. Really, for the competition that I entered in with the Department of Energy, we didn't even have to build a prototype. All we had to do was have drawings. But our students, they really like to get their hands dirty, so to speak. And so we kind of went that extra mile, built a prototype, did computations. That's a large part of the reason why we won the Rising Star Award.
Great, thank you very much. I've got one more question. Someone asked in the chat, how will you go about testing your devices in the ocean?
That's a great question. We are not there yet. It is, the more and more I learn about it, the more and more I watch my colleagues discuss some of the challenges associated with it. We know it's going to be difficult. It's not a calm environment. We have to deal with salt water. We have to deal with just the sheer dynamics of ocean movement, the pressures associated with it. How are we going to stabilize the device? I hope, my goal is that in the next 2 years, because we're 1 year behind now because of COVID in my mind, that we get something in the ocean. And I strongly think that we will find there's more challenges associated with than we initially anticipated. But there is a company from OSU, Oregon, that deployed a device in Hawaii recently, PacWave. I think what it is. My colleagues may be more familiar with this than me, but they actually deployed a oscillating water column off one of the islands of Hawaii. I think it was in December, so it's fairly recent that they did that. So hopefully we can gain a lot of information from that so we can be more productive and learn from some of the challenges that was associated with deployment of an actual oscillating water column.
Great, well, thank you very much, Dr. Atkinson.
OSU is a big one. I see that last question there. State, I hear a lot about they pretty with Wave Energy, they're pretty big, but some of my other colleagues may know of some other universities that are really big in ocean energy.